Hello, hello, hello.
Wanna be all in, but I'm guarded. Gotta be real cautious. Whenever the rain falling on this, baby it's falling. If I'm honest, wanna be all in, but I'm guarded. Gotta be real cautious. All of my words to you the hardest. All of my words to you the hardest. Wanna be all in, but I'm guarded, but I'm guarded. Gotta be real cautious. Whenever the rain falling on this, I run away for the longest. I wanna stay, but I'm guarded.
Drinking more alcohol for the past 5 days. Did you check on me? Did you check on me? I walk in the room, eyes are red and I don't smoke banga. Did you check on me? Did you check on me? Now did you notice me? Nobody will know the paranoia. Cause I put a smile on my face. Cause I put a smile on my face. Nobody will know the paranoia. Cause I put a smile on my face. Cause I put a smile on my face. I've been drinking more alcohol for the past 5 days. Did you check on me? Did you check on me? I walked in the room, eyes are red and I don't smoke banga. Did you check on me? Did you check on me? Now did you notice me? Nobody will know the paranoia. Cause I put a smile on my face. Cause I put a smile on my face. And if you know the paranoia. Cause I put a smile on my face. Cause I put a smile on my face. Drinking more alcohol for the past 5 days. Did you check on me? Did you look for me? I walked in the room, eyes are red and I don't smoke banga. Did you check on me? Did you check on me? Now did you notice me? Nobody will know the paranoia. Cause I put a smile on my face. The facade you can never face. And if you don't know me well, you won't see how buried I am inside my grave. Inside my grave. Drinking more alcohol for the past 5 days. Did you check on me? Did you look for me? I walked in the room, eyes are red and I inside me, babe. I've been drinking.
Just try.
And I just stand there. It's been a while since I heard my own voice.
Tiempo, energía con nosotros ríos y miel.
Yes, Freddie. Happy birthday, my bro. Happy birthday, JJ.
You're so much better at everything. Nice and clover in my chair, there's no compare. I adore you. Ooh, I adore you. I can't fuck, but you're ahead beyond your years. People try to find this thing you've always been. I adore you. Ooh, I adore you. And when you're answer, you walk through life just like a dancer. Like my way every day would be your parade. When you pray your answer, you walk through life just like a dancer. If I had my way every day would be your parade. Ooh, I adore you. Ooh, I adore you. And I pray you never lose your soul. I'm so proud of all that you are. Ooh, I adore you. Ooh, I adore you. I adore you. Ooh, I adore you. When you know your answers, you walk through life just like a dancer. If I had my way, every day would be your parade. When you pray your answers, you walk through life just like a dancer. If I had my way, every day would be your parade. Ooh, I adore you. Ooh, I adore you. are, proud of all that you are. I adore you. I adore you. I adore you. I adore you.
I will not stop, 'cause I move it. I will not stop, 'cause I move it. I will not stop, 'cause I pull the weight alive with so much juice. Move it. I will not stop, 'cause I move it. I will not stop, 'cause I move it. I will not stop, 'cause I
adore you. I adore you.
always, that you always, that you always know.
start looking at some code. Probably not gonna talk as much as usual. Maybe that will make the process go a little faster. We'll see. We'll see. Alright, let's just jump right in. I wrote some note down from the 2 or 3, is it 3 now? Source code reading sessions that we've done for the simulator. Also, the music is mostly for me to stay awake, sort of, because it was a little difficult to make the decision to do the stream. But yeah, I'm just trying to be disciplined about actually doing the stream every weekday. So that's the pain of discipline, I guess. You do the thing even when you don't feel like it. Anyway, so I wrote some notes down for the stuff that I've looked at so far, which is really just the entry point, but I think it gives an overall idea of what's going on. And I think going forward, we'll be looking at the specific modules. So today, I think we'll be looking at the shrink, and the shrink module is looking at the main, according the main entry point function, or what do I call it? File, whatever. The idea of the shrink is really, and I mean you can see it here. When you find a bug, you basically want to provide the most efficient way to go from some initial state to get to that bug, right? And I think we skimmed through what the shrinking plan was briefly yesterday before we left, and I think the gist of it was basically removed all the in-between queries that are really read queries, and it basically only keeps the primary queries of the property that is being tested. So if we take this for example, this here is the stuff that gets removed when you're trying to shrink the log of commands that lead you to the bug, because these are not concretely, or I guess even logically, contributing to the fault, to the bug, right? So there's no point in keeping them around as you're trying to reproduce the bug, because now you're just wasting time running these queries that have, functionally speaking, no bearing on actually causing the bug. So that's what the shrink functionality is for. Yeah, and if I remember right, no, I would say, yeah, they'll still remove all the select queries. Yes, that too. Anyway, so that's what we're gonna do. In fact, that's the only file. So I mean, technically, that's really it. I mean, logically speaking, that's what this is for. I mean, we can ask Gemini 2.5 what he thinks. Talk to me about the shrink functionality. Yeah, I think I mostly get it, but give me your take. Oh, and I don't know, I probably shouldn't be playing this music technically, but then again, it's not like I'm trying, like, I don't care about this video being monetized or whatever, so I don't think I'll get, I mean, so far I've played music and they've sent me copyright stuff, but not like as a strike, just that, hey, you're listening to this thing and blah blah blah, and the video won't be monetized or whatever. So I'm guessing the same thing will happen with this one. Yeah, I don't know. I just like having the music in the background. I need to figure out how to I mean, at least just me listening to it, maybe it doesn't play on the stream, but just having it is really helpful for these late night, I guess you can call them study sessions or whatever. Alright, let's see what Gemini has to say. Yep, making it easier to develop, for the developer to diagnose the root cause. The crucial piece of information tells the shrinker which interaction in your original plan was being executed. It contains interaction. Okay. Yeah, so you get the dependencies. The initial number of oh, okay, all right, in the plan total, okay. Remove all properties after the failing one. Yep, because we're never going to. I mean, as far as we're concerned, is those don't exist, right? They're beyond the scope of our target. Yeah, after the point of failure or unlikely, it keeps the failing interaction itself and everything before it. Okay. So now this is the part where you leverage your dependencies. Anything that does not contribute into, as dependencies to the bug gets also removed. So and this is happening at both ends, right? What we just saw earlier, this part here is the simplest one. That's the I don't know. I guess we tend to think of time going from left to right. So I guess in this case it would be everything to the right, starting from the index at which the bug happened, all the way to the right. That's gone, and then we go through all the stuff left and right, and we make sure that we remove all the stuff that doesn't count as a dependency of the expected bug outcome. The idea is that interactions operating on entirely unrelated tables are less likely to be part of the minimal bug reproducer. However, this is used. Yeah, fair enough. Might sometimes remove essential setup for the failing interaction if the dependency tracking is imperfect or is if indirect dependencies exist. Fair enough. Oh yeah. So yeah, this. Yeah, I think we did go through this particular thing yesterday. I think that was the last time we actually looked at. Anyway, yeah, we're moving the intermediate queries. Non-essential internal steps, yeah. Standalone select queries. Yep. Often used for observation and assertion. Wait, it says a select query could in some system trigger a bug by hitting a faulty index or a bug in a query processing. Yes, but I think within the particular context that we are in, I don't know. Yeah, okay. I'm just I don't think it's out of the question to say that in fact that the select queries can or should be kept as part of the shrunken plan. But again, I guess for a first version or first implementation version, I think this is a fine choice to remove them. Okay, this is straightforward. Heuristic based. Whatever operations during which these figures are applied can matter. Neighbors and restart while binary. These are common and effective. Truncation is almost always good. Removing unrelated operation is good. Simplifying complex operation is good. Okay. Try more combinations of a novel, not just fixed sequences of loops. Shrink properties by removing the extensions or shrinking the values. Oh. Yeah, but then, I mean, this, I don't know about this one. Because, well, okay, I also get it. Maybe it's that it's not this specific insert, this specific combination of input that breaks things. Maybe it's some set of possible values, and if you can find the most compressed version of a representative input, then you should just use that. So yeah, I mean, hypothetically, if using this or this trigger the same issue from an information complexity standpoint, you probably want to choose this because it's more, it removes unnecessary assumptions that you might make. About why particular input instances are causing a bug, right? Because I think sometimes when you're debugging or trying to fix something, it's sometimes the case that you fall into the trap of fixating on the very specific instances of the inputs instead of just thinking of them more as a thinking more in terms of the property of the inputs that's causing the bug, right? So there's the property, as in, you know, maybe it's that the function just doesn't work when you pass in. I mean, it's a very trivial and contrived example, but maybe that the function doesn't pass whenever doesn't work whenever you pass in two negative numbers. Now in the test that you're running, the values may be just, I don't know, negative 99 and negative 22. So a mistake, which again, this is a contrived example, but it's just to illustrate the point. You don't want to get fixated on the fact that, oh, negative 99 and negative 22 are what's causing the problem. It's like, no, what's causing the problem is you're sending it two negative numbers. So that's a more useful information to have than, oh, negative 99 and negative 22 failed. You know, that's not, from a systemic view of, you know, I don't know, profiling, debugging, whatever, understanding the system or the model, or having a good model of the system that's on the test. Understanding the properties of your inputs is more important than the inputs themselves. So I think this is what this is about here. Alright, so that was actually pretty straightforward, the shrink thingy. Okay. So now, I don't know, which one should I go, the model or the runner? Oof, that runner module looks thick. Maybe I should. Oh, this one is not slim either. So here we have the properties. Can't see anything. Let's see. Give myself some space. Trying to look at which module is the low hanging fruit. I think shrink was the low hanging fruit. I think all of the rest are actually, you know what? Fudge it. Try not to cuss so much. So I'm gonna use words like fudge. Fudge it. Let's just go with runner crate, a module, whatever. Module. Alright, so this is the entry point. This is relatively recent, 4 weeks ago. Does this say anything about the simulation runner? Bug base. Okay, loaded or unloaded. Production plan runs. Okay. Then you have a bug run. may or may not be an error, and the CLI options that were used. So is this okay? That's from the CLI here. Okay, this is straightforward. Get the seed of the bug. Oh my gosh, everything hurts. Did a bunch of tire flipping this morning. We were so we're doing the flipping as a group. There were 2 groups, 2 tires, and you basically go in a line. You flip it, you go to the side, you do a burpee, and then you go right back to the end of the line, and so the line keeps going. Everybody gets a turn, and then it goes around. You go back. Anyway, did that first round, and on the way back, I don't know what got over me, but I decided to just start and not stop. Basically, I took over the thing because I had one of my gym mates on the other end. He's, I would say, overall stronger than me. Maybe not as doesn't have the same endurance, but definitely stronger. Anyway, I just started just flipping it over and over and over. Anyway, that may have been a mistake a little bit, because I am sore. Hopefully that helps with going to sleep in several hours. What time is it? Well, several hours, really. An hour and a half. Which is why we need to get through this. Okay. Definitely get through bug base. And then we'll see what happens. Alright. So get the state of the bug. Access, bug base. Wait. So this is bug. Bugs that are loaded or not. A loaded bug has bug runs. What about an unloaded bug? Is just a thing with a struct with a seed. Okay. Now a bug base has a path in the file system. Well, presumably there were bugs. Okay, I need to keep remembering that. Bug. There's a difference between a bug and a loaded bug. So to create a new one, you need a path. That makes sense. You read using the path, see if it's a directory. Wait, what if it's not? Am I crazy, or it doesn't handle that case? Wait, so this thing can fail silently? Is there a silent failure execution path here? As in, what happens when the reader fails? Looks like the path just gets returned with an empty map of bugs. I mean, it's there. I guess I just using a rubber ducky here just to make sure I'm not insane. No, I'm not gonna change it. I mean, let us know now. I guess I could submit some sort of issue ticket, whatever, but I just wanted to double check. Yeah, I mean, yeah, it might be the desired behavior. It's just, I mean, assuming that the callers of these know this behavior. I mean, it's not always obvious, right? Especially because here you have a result thing, which means that you would kind of suspect or expect that if opening the directory at the path that you gave it fails, then you get an error. Yeah, there's a lot of happy path and just moving on thing here. Because I mean, even this, if this fails, as in, you know, the predicate here is not true, then what? You know? I don't know. Anyway, so let's say it works. You read the directory, you flatten it. Wait, what does flatten actually do what I think it does? I mean, yes. I don't know. It's just one of those things. It's like it's nice to always double check that your assumptions are not misguided, even sometimes when it feels like it's something trivial. What is a file type here? What is a multi? Okay. Okay, I see. Alright. I mean, again, looks obvious. Sometimes you just want to check the API. And it's nice when you have documentation attached. I mean, obviously this is a standard library, so sometimes, you're working with a crate or some third-party thing and you see it's there, and sometimes you check the internals of the implementation and you may be doing something that you were not expecting. Anyway, that's just to say that sometimes it's useful to take the time to understand how the API of external libraries are being used in the code. Okay, so you have the file name. So all this is parsing logic. Okay, so wait. Gosh, okay, I just realized why it's all happy path thing here. This is only relevant when it's reopening. Gosh, I don't know why I didn't clock that sooner. Actually, this is fine. Yeah, it's like recovering from a crash or whatever if you have an LSM log structured merge tree, LSMT, or any database really or whatever, where you either are creating the instance or you're loading from existing storage. Not even going with databases. I think just in general, let's say even in a front-end application, a React application where you may have persisted some stuff in local storage, and on page reload, you wanna, let's say, a form, right? Some form with, I don't know how many fields, non-trivial amount of fields, where it will really suck for your user to have to restart because they, I don't know, accidentally reloaded the page, or they got redirected for whatever reason. Anyway, and then just having to start over on page reload or whatever. So instead of that, on page reload, you can check if there's been some data that has been waiting to local storage to maintain some kind of state for the form. If yes, then you load that in, so that you, I guess I think they use the word hydrate often for that sort of thing. So yeah, you hydrate the state based on stuff that was persisted. So this is fine. I misunderstood. Yeah, okay. So yeah, just to reiterate, it's fine if this fails. Really, it will just mean that it's not there, or at least that's the fault model that I'm assuming the author here is going with. The idea that this is only gonna fail if, fail. Well, yeah, no, that is a failure. Is it a failure? Yeah, I feel like that's just being pedantic or whatever the word is. Anyway, let's. I think I've made my point. Let's move on. Okay. Let's see if we can switch things up.
And this is our soft.
Alright, let's go with that. So, I mean, just by looking at the comments here, I think these two are meant to be the sort of the same. Except that here you explicitly provide a path. Here it's and it's infrared, I guess, for you. Projector. What does? Oh, okay. That's from the standard library, I think. Wait, is it? Where's that coming from? Oh, I'm curious. Okay, so this is, in fact, a standard library thing. Okay. Potential paths. Okay, so the Limbo project, the home directory, or the current directory. Okay, that's sane. That makes sense. Looking for a particular path, and if it's there, do your thing. Wait. Oh, and this is a... Okay, you just find the first one. Whatever is the first one that you find. You exit with it. So if you made it here, you couldn't find anything. So if not, it's gonna try to create it for you with this precedence or preference in terms of the path, the paths that it's going to attempt. And then there's the exit, and if you made it here, then something went wrong. So this is basically the same as the first one, at least in the first part, and then the second part is where they go to they make it interactive. Alright, makes sense. Pausing. Limbo. Failed to get home directly. Wait, why not just extract it the same way? Why fail here? Because you didn't find it. That feels like some inconsistent. That could use some inconsistency issues. Subtle. One would even say trivial, but not sure why we're not using the same thing to get the home directory. Alright, if it exists, then yell about it. If not, do your thing. Alright, now we add a bug. It's its interaction plan, its error if there is one, and the CLI options that were used to run it. Adding bug received. Alright, so first it checks if it already exists. If yes, you load it. Oh, okay, yeah. Wait. This is interesting. Why are we, if we already have the bug here, why are we going and loading it again? What is this doing? Yeah, let's yeah, it's returning a bug, which let's start check. Can either be unloaded or loaded, and if it's loaded, let's just use that. Why are we doing this whole dance here? Well, I guess this is a more sophisticated um, handling. So if it's unloaded, what are we doing here? We are trying to load a plan. Okay. So there's the existence of the bug. Okay. All right. I think I get it. You could, it's some sort of lazy loading pattern thingy. Well, there is a way to know that something exists without going through the trouble of actually materializing it fully. Okay. So there's the plan. You have the runs. And then you form the thing, and then you finally make it loaded, and now it's available to access. Like now it's in memory instead of being in storage. Okay. Alright, so we got the bug. If it's we load it. If it was already loaded, it just returns the loaded bug. Okay, so when you say add, okay, so I guess you're merging an existing record with some new added information. Otherwise, you're just creating a new one. And in either branch, you end up saving the stuff into the database. Okay, so save seems pretty straightforward. Excuse me. Why save a specific bug? I mean, this feels like it's more of a checkpoint thing, right? You've done a bunch of stuff, and now it's time to just flush whatever you have in memory to disk. Well, I guess, okay, never mind. That would be wasteful. If you had to flush everything every single time, you only want to flush the stuff that has changed. Basically, whatever, some sort of buffer that where you buffer. Well, okay, the hash map here is not really a buffer of a case of buffered IO, in the sense that it definitely has stuff that doesn't need to be flushed, and only a fraction of it needs to be flushed. And what I just now originally was going to argue for actually doesn't really make sense. Excuse me. Have the bug path. Have the bug directory of the C text. Okay, I mean, all of this is straightforward. Okay. Straightforward stuff. Yeah, I don't think there's much to say here. It just flows as you would expect, top to bottom. The order in which things are being done makes total sense. Yeah, okay. We already looked at that, and now we're looking at working something as successful, or a run as successful. So we get the bug. If it's not in there, we remove it, because we there is some sort of inconsistency that we want to remedy. If we found it, then we load it, we have a bug run, no error. Oh, okay. The assumption here is that, well, I was gonna say the assumption here is that you're basically replaying a bug, and you've made changes or whatever, and then you've hit, or you've come to a place where you will run the bug, and now it's gone. Basically, you fix the bug. This is what this function is doing, I believe. I don't think it applies to, it shouldn't apply to bugs that have never been logged or added to the bug database before. Makes sense. We're using the load bug function over here. Okay. And to list the bugs, you load them and then you iterate. Alright, let's see. So the path, the DB path. Makes sense. Straightforward. Get current commit hash. Okay. Straightforward as well. All right. Bug base is down. Question is, do I stop here? I'll go on to something else. Maybe not CLI. What's the file situation? IO is probably interesting. Well, if we did not want to look at more Limbo code right now, what should we do instead? I think we have an hour max left. So what are we gonna do? Just we could look at some deep learning stuff. There was a conference. Yeah, I think it's this. We should do that. Look at something like Franca conference then. Did I? I think it's which. Okay, so I do have it. .NET something. Oh. Apparently I don't. Okay, never mind. Something that I've been meaning to do, I think. Well, I wanted to install TLA plus and actually, well, the problem is I don't like installing things directly on this account. I like to do it from the main account on this computer. So I don't know if I don't think I should do that right now. Okay, let's just do this. Let's watch this.
Design framework that we built for them that maybe makes it a bit easier for you to build larger distributed embedded systems. And I want to start with complaining a bit about distributed.
Again, just for some context, I've been doing videos on lingua franca. I have a whole playlist where we go through the manual basically. And after, well, at least in the process of doing that, I got the bright idea to try and rebuild, I guess, port the Limbo simulator into a lingua franca program. I have no idea how that's gonna go. there's only one big issue right now, which is that I'm not able to run the simulator on my machine. I still haven't been able to do that, and it's because of some package thingy situation. Yeah, this something thy sim util. It's not found. I'm hoping that that gets resolved, because I'm not sure that I can truly, well, I probably won't be able to truly work on a project without it. I think it's a little asinine to port over a project that you can't actually run. Not saying it's completely impossible, it's just, why? Unless you absolutely have to, and gun to your head or whatever pressure you have. So I don't know. It may be that I pick something else. I mean, it's still nice to go through the simulator code here, so I'm not really complaining. If I go through all the code here and by then I still haven't found a solution to the installation process, will still be fine. Like I'm okay just reading the code, and I can still use that knowledge to potentially make some contributions on the open source project. So either way, this is not a waste of time. But yeah, so that's the context around wanting to watch this particular video. I try to keep track of content related to lingua franca, the programming language. They actually have quite a bit of research papers. I think I only read one of them. And I think there was somebody who actually did the whole, was it master's or PhD thesis on distributed system stuff with lingua franca. So yeah, they have a lot of content. I mean, I don't know. I guess you can qualify what a lot means, but they have enough out there that if you're interested in the language and the runtime, you can get something out of it. Like, it's useful. And it gives you an idea of, what you can do with it. So yeah, if the limo thing doesn't work out the way I planned, so I'm either gonna do some deep learning stuff, or I want to get back into the Kubernetes stuff. We started doing Kubernetes early, like a couple months ago. I've been doing some practicing, but like off stream, just regular practicing. So I think maybe will be an interesting challenge is to see if I can build some sort of toy program that represents a Kubernetes operator. I mean, for the longest time, I've tried to just not care about Kubernetes, but the truth of the matter is it's one of those things. uh, you can. There's a lot of shit to talk about, or to complain about, but it's still like in terms of deployments, it's it's the thing. And just having a solid understanding of the fundamentals of it, even as a developer, I think that's useful. But I don't want to take the full-on DevOps, or even worse, the memorize stuff for a certification route. I very much want to take the software / developer distributed systems approach, which would, I think, entail basically building either a scheduler or a controller, or I think this idea actually came to me a while back. So I work on this open source project, Wasm Cloud, and there was actually an operator here. I think at some point I wanted to see if I could run it through. There was another project called I think it's Anvil. Yeah, Anvil. Framework for So somehow use this to verify this, right? And I feel like to really do a good job of that, having a good understanding of the Kubernetes API would help. So that will be one thing, that will be a goal on this journey of becoming, to know enough to be to know enough to have a useful conversation about Kubernetes. But also just, again, can you build a Kubernetes operator that, or at least a Kubernetes operator simulation using lingua franca. So basically I want to build something with lingua franca that's interesting. I guess I don't want it to just be a hello world type of thing, and maybe I may change my mind and just try to do something less demanding. Anyway, so that's the context behind the whole Limbo code, source code reading, and now watching some lingua franca video, and
systems, because if you build distributed systems, especially like on a spacecraft or some other vehicle, most of the time you have very high platform heterogeneity. You have different protocols, some from CAN bus to some to Ethernet, to all kinds of different protocols that you potentially have to use. Your topology most of the time is completely implicit, right? You build your individual nodes. I don't know, node 0, node 1. Maybe you have some library that binds those systems together, but and then maybe one good day you take yourself a whiteboard and draw out how your network looks. But this is implicit, right? And it also gets increasingly more complicated. The larger your system you get, potentially more heterogeneous you get. You need to keep all your nodes in sync, that they're able to speak to each other, they speak the same protocol, the messages have the same semantic meaning, and so on. And so we would like to improve this. And what we would like to do instead is do design automation, some model-based design, where we start with a model, that is this little green box there. where you express your whole program inside this one model. Your topology is completely explicit from the beginning. And the point is of doing this model-based design approach is that you can, take care of the logic of your program. And then our tooling, here represented by a compiler block, then actually takes care of synthesizing those different nodes in your system that you then can roll out and deploy. And for that, I want to focus on the first block here a bit and speak about this. How do we actually describe distributed programs? And a good place to start is models of computation. So if you do programming or any computational heavy things, you need to think about models of computation. And here, this graphic basically categorizes different models of computation into 4 categories. Timed, so do you have some semantics of time inside your model? Scalable, right? You can add more nodes to your system, remove them. Is your model deterministic? So given some sequence of inputs, does it always produce the same sequence of outputs? And reactive, right? We're building flight systems. You need to interact with the real world, and there you need to react in some time boundaries, so you also want to have those real-time properties. And here are now different models of computation, synchronous data flows, threads, PubSub, and for example also actors, which maybe some of you know. For example, F prime is very actor-like. And actors are those little cyan boxes there that hold state, and they have ports where they can send messages, receive and send messages to their neighbors. And then you have things called actions that react on those incoming messages and then execute some code. And the problem with this is demonstrated by this little graphics down there, this little relay examples. We have 3 actors, a source actor, a relay actor, and a destination actor. And the source actor now sends 2 messages to both the destination and the relay. The problem is now that this program is inherently non-deterministic with the actor framework because the execution inside the destination actor fully depends on the arrival of messages. So if you have potentially changing latencies inside the destination, or the relay takes longer or shorter, you get different arrivals and different arrivals of the messages, and therefore potentially different executions, and therefore non-determinism, which is maybe not what you want. Non-determinism makes it very hard to debug your system. It's way more harder to test it. It gets flaky and so on. So determinism is a property that we want, and maybe let's take a look at another one. Synchronous languages. The French do that quite heavily at INRIA. Here's, for example, a little SQLite snippet that toggles an LED every 50 milliseconds. And you now can stack those loop statements into each other and those wait statements. And here you have a very clear semantics of, for example, logical time, right? You have, right, in your program, you specify every 50 milliseconds that the signal should invert. Problem is, those models are not particularly scalable. They are constrained to single cores. You cannot really, how would you go about distributing this kind of stuff? So what is this question mark in there that actually fulfills all of those properties? And that is the reactor model of computation, was developed by mainly those 3 guys. And this fulfills all the properties. And if you visit this website, alaflang.org, it states right on the top there, lingua franca is a polyglot, so multiple languages, declarative, like a programming paradigm, coordination language for real-time concurrent and distributed systems. And that's quite a lot, so let's unpack this a bit. And look how, for example, this model of computation looks. And here we have reactors that are like actors that hold state. You have reactions instead of actions that where you put, as a programmer, you put your user logic, and this logic can be expressed in different languages, C, C++, Rust, and so on. And they have, so this is this polyglot property, and they have a total order inside a reactor. So they have this, there's a dependency between those 2. But then you also have other things that you don't have in actor frameworks, for example, timers. You have a timer that has an initial offset of 50 milliseconds, and then triggers this reaction 2 every 250 milliseconds. And you can now take those reactors and, for example, compose them to larger systems. Here you have some very classical CPS example, where you have, 2 sensors. One reads its value every 100 milliseconds, the other one every 50 milliseconds. Those sensor values are forwarded to this processing reactor that then implements some control logic and then drives this actuator. And this diagram here is generated from the source code that you see on your left-hand side. That's some tooling that we have. And even so, and maybe to give you some intuition why the determinism property still holds is, in the actor, it really only depended on the arrival of messages. In lingua franca, so you have potentially 2 ways this could execute then in reality based on this arrival time. But in lingua franca, there's only one, this model of computation restricted to only one valid sequence of executions, independent of in which order those messages arrive. And here you see the relay example from the actor slide written in lingua franca, that you see the source also produces events that go to the destination. But here you have this clear ordering of the reactions, that reaction 1 always needs to execute before reaction 2. So you have, by the model of computation, this enforced that this is executed in the correct sequence and not in some sequence that you maybe not predict. Yes, and how you should think a bit about this lingua franca and this reactor model is that this works a bit as a this declarative property that is close to a specification, right? You write inside your program what the timer should happen should fire every 250 milliseconds. But if this then actually happens in reality is then a bit of a separate question. And for that, for example, this language also provides properties like deadlines, right? Deadlines, for example, say this reaction should shoot at T 100 milliseconds, but for whatever property this now gets delayed and the reaction would execute at 160 milliseconds in real time, then we, for example, can provide you with deadline handlers where you then can handle this fault and do some, do some cleanup and try to fix the problem that you have right now. And of course, also in reality, you have asynchronous inputs, and you need to some way to introduce this non-determinism into your system. And for example, there's also language concepts. And with that, I want to motivate to give this as an input to our tooling. There's of course way more stuff inside this model of computation that I don't have the time to really talk about, but I'm happy to talk about it afterwards. But this is now our input to our tooling. And then we have what we call the lingua franca compiler, which translates this lingua franca code together with your logic that you have inside the directions into semantically equivalent C code. And then we combine it with a new runtime that we write, that we build, put it together in the target basically for whatever platform you're currently building for, Sapphire or whatever, and then you get some binaries. And I want to talk about this new runtime. We built a new runtime especially for embedded systems called Reactor Micro-C, so targeted at microcontrollers, most of them single cores or single or dual cores, a couple of kilobytes of flash storage, a couple of kilobytes of RAM. Your networking also looks very different. You have way more serial protocols, I2C, SPI, UART. You have different wireless setups. Think about LoRaWAN and in general those IEEE 802.11 protocols. And because we built this runtime from scratch, we can also do very cool things. For example, no mallocs. This entire runtime works without any mallocs. The code generator pre-allocates everything, which is pretty nice because we can reduce potentially so those dynamic faults that can occur at runtime. And the application that we're targeting, I think IoT is pretty clear, right? You can deploy this stuff, you can write to distributed systems, but also drones, for example. And the idea behind, for example, this drones is that you treat the controller that runs on the drone and the controller that, for example, runs on your little joysticks. You treat that as one program. And then this tooling allows you basically, you treat this as one program, and then the tooling basically produces binaries that you can flash onto your little joystick controller and onto the drone itself. And so you can sketch those larger distributed systems quite easily, but everything basically that has where you have embedded systems that are potentially distributed. And what is the purpose of this runtime? So we have this generated code on top that the code generator spits out with some networking configuration, and then there's what we call the environment, where, for example, the scheduler sits. The scheduler executes this according to the Reactor model of computation. And we also have other features like potentially clock synchronization, which is needed for some nodes. And for example, we need, of course, some logic to handle incoming network messages and so on. And below that, we have, like most operating systems, we have a platform abstraction where the user needs, we provide essential functions that we need from every platform. Things like we need some way to sleep, we need some way to get the physical time, we need some way to asynchronously wake up, and some synchronization mechanisms. And of course, we need abstractions for different network technologies. TCP, we currently support TCP/IP, UART, and co-op over wireless protocols. And those are currently the platforms that we support. Riot is an embedded operating system. They always have, if IETF standardizes anything, most of them, they already have support for it. Sapphire, I think, is pretty well known as this big embedded operating system that is supported by a lot of the big vendors for boards. And we also support Raspberry Pico and Linux. Yes, and so we built this design framework where you can build lingua franca projects, but now we also want to make sure that the design framework is actually easy to use and nice. So we started building different applications, and the thing on the left was the first thing that we built. It's a couple of those NXP boards strapped together, and then we could build lingua franca programs that span those 3 picos. The second one is what I will talk about more in detail in a second. And on the right-hand side, that's we're also right now basically building on wireless stuff. And the one in the middle is for basically testing our runtime implementation for serial communication and potentially features relevant for fault tolerance. And a bit why fault tolerance is interesting to us, because it very much fundamentally, so in lingua franca you have this timing semantics, and in general you can express lingua franca quite nicely this potential trade-offs between consistency and availability, because if you want to have consistency, determinism is already a very nice precursor to that. And in fact, if you now do fault tolerant software, you are, it is, for example, think about like a leader election protocol or automatic failover. If your main flight computer goes down, you are interested in both properties, consistency, because if you want to have a leader election protocol who is currently your main controller, it only should be one. So you need consistency between those nodes, that they agree on a value. Or if you do failover, you need to agree which node now jumps in, or where a new thing gets spawned. But you also want availability, because this failover should happen quickly, preferably like in the millisecond range and not like minutes. So you have this fundamental trade-off between availability and consistency, and that's what the CAP theorem is about. It was originally done for databases, but it still holds. It's a quite fundamental theorem where it basically states if your network has some partitioning, which can be, for example, latency, sufficiently large latency, then you need to trade off consistency against availability. So you have basically this spectrum where you can design different where you can build different controllers or different failover programs that basically land on somewhere on the spectrum. And so we basically built a small PCB to test this with those 3 picos. Every pico has this brightness sensor, like an attached sensor to it that you can read with I2C. There's some status LEDs below it. Then those central LEDs, they can be controlled by every individual pico, so those are like your actuator from the CPS example, like this is your common resource that technically every controller can access, but only one should. And then you have those little blue switches to simulate node failures. So one of the node dies, or you can simulate network failures. And then, of course, you want to potentially have automatic failover. And so this is, for example, the program how it looks that runs on one of those picos, where you have this failover reactor that exchanges control information with its left and right neighbor. It produces some basically status signals that we forward directly into those pico reactors with the on the set input. And it also provides forwarding information where basically it runs this leader election. Where's my current leader? Do I need to send my sensor value from the sensor reactor to my left, to my right neighbor, or my current leader, so it needs to send it to myself. And so all of the programs, for example, send automatically their sensor reading to the main leader. The main leader has a little LED controller and controls those 3 center LEDs. And now you can check this failover reactor implementation by then turning and playing with the nodes. Basically turning off or testing different scenarios. Yes, and you can now basically take this one node, right, and basically build your topology out of it. So you have 3 instances of this redundant node with parameterization, and you also parameterize all the network, basically if it's a UART device or if it's potentially something else, the baud rate, how many, if you want to have even, odd parity, and so on. And you wire up all the input ports from the program, and then you can, of course, also draw that as your big topology. You can take this big topology, throw it into the little compiler that translates it into correct C code. You can run with the new C runtime that we built. You can use one of the newer, basically your platform-specific tooling, if it's like the Raspberry Pi Pico or the Riot OS or the Sapphire or potentially Future. We also support some embedded, some bare bones targets, and then you can flash the binary onto your program, onto the board, and you can run it. And I have the board with me, so I'm also very open to show it off. I don't know, the next break to you. And with that, we achieved our initial goal of doing proper top-down design. Those are my partners in crime. And with that, I want to say thank you.
Any questions? All right, while our mic folks make their way over there, we'll take one from Slack here, from George. When you say the compiler and runtime try to execute by deadlines, what is the recovery behavior?
By what?
By the compiler and runtime try to execute by deadlines. Mm-hmm. What is the recovery behavior when the deadlines are exceeded?
This is basically, those deadlines are, they are basically what you as the programmer, you are, right, this is the system design framework, and it works a bit, those deadlines work slightly a bit different than your classical real-time deadlines, where you don't do, or you currently, you could think about doing it, but currently the scheduler doesn't implement, doesn't assign priorities and does scheduling, tries to, preferably execute those reactions faster, or get to those reactions faster. How those deadlines should be understood is that they specify, if your program, if what you specified in your program definition goes, of course, from what happens in reality. So imagine you specify a thing that should happen, every 10 milliseconds, but there's other stuff in the system that should happen. So it doesn't execute every 10 milliseconds now. It now gets lagged behind. And so you can specify those offset values to handle that if you basically, if you're in reality, then your system basically goes too far off course or starts generating too much lag that it cannot hold your deadlines anymore.
Okay, so just to make sure we answer the question, it sounds like the deadline, if the deadline is exceeded, you define the behavior.
Yes, you then write, as a programmer, can write those deadline handlers that then execute what then you can do at your recovery behavior and so on.
Okay, thank you. One from the room? Oh, there was a question back. Oh, okay, right here.
I see this 50 millisecond clock, and in the example with the 3 Pico boards, right, Raspberry Pico board, you have the times in the code. Yeah, there's a code, you have multiples of 50 milliseconds, right?
Yeah.
Do you have a central synchronization mechanism? I see that little clock icon on each Pico board.
Yes, so
right?
how basically it works, right? This, there's the schedule.
Take it over.
So, of course, right, those nodes need to be properly synchronized. And that's, for example, why also in this little diagram about the runtime, you saw, for example, the clock swing stuff, because Picos have very bad physical clocks. So, for example, we need to provide some way of clock synchronization. But if you basically specify this timer here, you have this duplicated 3 times. And this timer, in this example, here literally just toggles like a status LED every second. And of course, this needs to be synchronized because according to the specification, every timer, every program should fire at the exact same time. And so basically, and that means, right, that all of the LEDs then also should basically lighten up at the exact same time on all of those different nodes of the system. Got it? Yeah, but that's why we then, for example, provide clock swing features that we then, but it basically, right, you have the logical timeline, and the execution on physical timeline should be as close as possible to what you specified inside your program here.
Thanks. If you have already such a, let's say, logical framework of describing the timing behavior, do you have also a chance to do scalability analysis on this one?
Yes, you can look at, so there are different works. Currently, this runs on a dynamic scheduler, but you can look into how this gets scheduled. Yeah, but there's also work from colleagues in this room where, for example, look into, for example, pre-compiling the schedule into a static scheduler that then gets executed, where you basically have it already fixed, and you basically just encode a fixed scheduler into the, basically generate a fixed schedule at code generation time. But yeah, clearly. And of course, if you add worst-case execution times to those reactions, right, then you can properly analyze those programs, like, assuming those worst-case execution times, then you can basically add together traces of those reactions, right, and see is this actually a feasible schedule or not.
All right, that's it. Thank you. Give it up for Tesla.
Thank you.
That was I think that was an introductory talk on the language. I don't know. I think I was expecting a more focused and specific thing, but I mean that was fine. That was definitely fine.
Is everyone awake? On the count of three, let's say flight software. 1, 2, 3. Flight software. Now I know you're all awake. So we're here to talk about flight software. My name is Thea Martin Gauthier. I'm the HPSC software architect. I work on a very small team of people in conjunction with a very large team of people at Microchip Technology. And we have developed this processor called HPSC, High Performance Spaceflight Computing. This is a project funded by NASA through STMD's game-changing development. And I'm going to talk a little bit about the flight software and software aspects of it. I see some of my compatriots in the audience. Some people from Microchip are here, which is lovely. It's going to work. Does it work? It doesn't work. Oh, well. So here's the agenda. I have a lot of slides to get through, so I'm going to talk really fast. In general, I talk pretty fast anyway, but I'm going to try and talk pretty fast. I hope that's okay for all of you. So what is HPSC? HPSC was engineered for the AI edge. If we're talking about high-performance computing, any kind of processor that you put in space that's designed to do autonomy or AI has to have significant high-performance computing capability. And we think we put this into HPSC. HPSC rivals a lot of GPUs, commercial or currently available GPUs, and also desktop processors. We are measuring HPSC all the time. We do a lot of different things to measure HPSC. Well, we did a lot of different things to measure HPSC while we were developing it. HPSC has incredible performance, 64 gigaflops of double precision, 128 single precision, and 256 half precision gigaflops. It's designed for AI workloads. It's also designed for doing high-performance computing in space. You can make a high-performance computer and put it in a hab or on a gateway with HPSC, and you can use different kinds of commercially available or open source software to meld all that together and make it look like one big computer. HPSC has significant fault-tolerant and flight software features, and that is one of the reasons why I'm here to talk about it. I don't imagine that any of you are HPC people. Who's an HPC person? One person, that's it. So you're all just flight software people. So do you dream about command and data handling? Okay. I don't know. So my background is in high-performance computing. I'm basically an applied performance engineer. I used to work in the applied performance group at Intel a long time ago. I don't really do that. I don't work on Intel stuff anymore. I mainly work on RISC-V and ARM architectures now. HPSC is very good at doing lots of different things. And one of the reasons for that is you can scale HPSC up and down. It's got a lot of ways to turn it into something that you would like to have it. You can switch a lot of HPSC on and off for various reasons. It can be in a rover, a heli, a lander. You can make high bandwidth instruments from it. You can put it in small sats. And it has a way to tweak its power to do almost anything you want. You're all taking pictures, but these slides are available. That's okay. I'm here to tell you that HPSC sets the bar for advanced autonomy at the edge. There's no other currently available nor future planned spaceflight processor that has the features that HPSC has, and I hope to convince you during this presentation. There are 6 big things that HPSC, the 6? Yeah, 3 and 3 is 6, right? 6 big things that HPSC offers. It's designed for high-performance autonomous spacecraft, and there's a lot of features for that. It's got advanced autonomy through its AI capability. It has serious fault tolerance, and also it's one of the first microprocessors, commercial microprocessors in existence, that has ARINC 653 built inside the processor. Significant time and space partitioning as well. Well, I said time, but it's a rad hard by design using multiple hardening.
Are they going to talk about that part?
It's a rad hard by design using multiple AI capability. It has serious fault tolerance, and also it's one of the first microprocessors, commercial microprocessors in existence, that has ARINC 653 built inside the processor. Significant time and space partitioning as well. Well, I said time, but
time and space partitioning. I wish you could. I wish you would talk more about those specific aspects.
It's a rad hard by design using multiple hardening techniques, and between NASA and Microchip, we're developing a huge ecosystem of partners to bring this capability to all future spaceflight. Also, the software stack, which is where I come in, is one of the most advanced and modern software stacks. I don't know about y'all, but I hate embedded development. Who hates embedded development? Yeah. Who has nightmares about cross-compilation? Thank you. I feel like my life is an endless succession of resolving dependencies on the target. Okay. Enough about that. What's so cool about HPSC, you asked me? HPSC has a lot of key features. First of all, it's a 10-core processor. There's 8 main application cores. There's something called the system controller, which is designed to monitor the health and safety of the processor. It's on all the time. And then there's a security processor, which takes care of security stuff. We're not really doing a lot of security right now at NASA or JPL, but we can see that coming up. And so HPSC has very interesting and lovely security features. A lot of this has, we took a lot of advice from the DoD and also from Microchip's partners to understand what needed to go in there, and we think we put that in there. The other cool thing about HPSC that maybe you didn't know is that there is a complete TSN, 240 gigabit enterprise-grade TSN switch. It's actually from the automotive line of Microchip products. It's an ASIL qualified chip with RDMA support, and I'll talk about RDMA support in a second. Loss of fault tolerance, radiation tolerance, dynamic power profiles, and precise power control. You can turn on and off almost anything in the chip that you like, when you like, to do what you like, which is important. And I already mentioned defense-grade security. Lots of stuff over here. I'm not really going to talk about it. You can sort of look at it. So here's what I call the fault-tolerant pyramid. Starting at the bottom with process and technology, and also moving up through different things, we have a lot of fault-tolerant features inside HPSC. Most of them are built into the device, for instance, like the kind of flops that we're using to create the device, or the node that it's being made on. Hardware scrubbers are working in the background. Some of it is more explicitly under software control, and a lot of it is for high availability, for failover, for monitoring the device, and for doing really other interesting things like NMR applications, which HPSC can do. We have dynamic power control. So there's 70 active gated regions on this chip. If you don't want the Ethernet switch on, shut it off. If you don't want endpoints on, shut them off. If you want to turn PHYs off, shut them off. If you are not interested in using the chip in a certain way, you can turn it up and down depending on how you want to use it. So there's a very small standby sleep mode. It will just sip power, or you can run flat out and get the highest performance that you want. And that's the sort of top line numbers that I talked about before. So you can tweak these by mission phases, and I'm going to talk about that in a second. One of the key defining features of a high-performance computer is how fast you can ingest data and how fast you can get results, which I call time to value. So HPSC, due to its switch and due to its RDMA capability, can sync 80 gigabits per second into the switch without CPU intervention using the devices that we have on here. And so what this means is that if you want to make a high throughput sensor, or you want to make some kind of large star array, or you want to do some kind of science where you have high bandwidth sensors, which is really what HPSC was designed for, you can ingest that data very quickly, and the CPU does not have to be involved with that. So you'll see a lot of spacecraft processors, and they have a 1 gig Ethernet, or they have two 1 gig Ethernets. We have 16 ports of 10 gig TSN Ethernet on this switch, and another 4 endpoints for that. So it's a huge amount of data that you can ingest with this. All for TSN, time-sensitive networking. Who's familiar with TSN? Some people. TSN is just a way to control the timing of things on the Ethernet network. Guarantees delivery of time, guarantees delivery of packets, so it's very sensitive to the needs of a spacecraft. One of the coolest things about HPSC is due to its architecture, you can split HPSC up into many different ways. You can split it directly in half. You can have DCLS pairs, which are dual core lockstep, which is where one core shadows another core, and if there's any execution mismatch between the two cores, it will squelch the output of the core so that bad data does not get into the rest of the system. There's lots of different ways to set up HPSC, and most of the OSs support all of these different ways. In reality, though, I think we'll probably use between 1 and 4 of these, although all of them are possible. The nice thing about some of these is they allow for high availability or failover configurations. They allow for things like mixed criticality. So if I want to split HPSC in half and run 4 cores of Linux on one side, flat out doing AI/ML work, but on the other side, I need to land the spacecraft with some kind of real-time OS, I can do that. And the two won't intermingle because I've split the architecture down the middle. The other interesting thing about HPSC is you can have many, many different configurations of HPSC on tap. And so each one of these configurations is a confluence of all of the different operating systems, all of the data, all of the pieces that would get loaded into the cores and execute. And then under flight software control, you can ask HPSC to boot to the next mission phase or to do something different. So for example, I'm cruising on the way to where I'm going. That's one software load. And then I want to land. That's another software load, which much higher criticality. And now I'm on the ground. I want to move into a system check mode where I'm going to check out everything. That's another thing you can do. So you can move between these, and you can get precisely what you want with the kind of power control that you want for whatever mission phase you're about to execute. Okay, so we're here to talk about software, right? So HPSC embraces modern high-performance standards, which means we have modern compiler, LLVM. We have the latest versions of LLVM, the latest versions of Linux. In fact, if you're using Linux and you're comfortable with that, you can fly any language you want. I think Kelly was talking about her engineers asking her if they could fly different languages. You can do that if you want. HPSC has broad system support and a hypervisor also. We have Zen hypervisor on board. So here's a nice logo array for you. I didn't show one yet, but this is my logo array. Most of HPS software is completely open source. There are parts that are not open source, but they're not that important for software development in terms of the day-to-day of what you have to do. So for example, all of the changes for HPSC and the SoC for Linux will be upstream to Linux. Same with RTEMS. The Xworks is, of course, a commercial OS that that will be handled separately. And we also have bare metal available. So speaking of these things, this is the scope of support for HPSC. We have a complete Debian distribution. So if you get an HPSC evaluation board and you boot it up, you're booted into Debian. Instead of resolving dependencies by cross-compiling, you can just apt-get install whatever dependencies you want. And then, when you think you got your software load, you can make your own custom OS with Yocto overlays that we provide. So you can go from a full-fledged dev environment for Linux down to a very cut-down one with Yocto. And the Linux that we're using since, I think, was 6.13, Ken, correct me if I'm wrong, we get the RT patch, which is mainlined up in Linux. So the default Linux OS will be RT. VxWorks, of course, VxWorks 7, RTEMS, and Zen. So you can run most of these OSs on top of Zen as well, or you can just use the ARINC 653 Zen support. And we also have the Sci-Fi bare metal SDK available if you want to run bare metal, or if you've got very, very, very tight control loops, 1,000 hertz, whatever control loops, you can do it that way. Language support, all the usual suspects. C and C++, which we'll never escape from now until the end of time. One of the coolest things about HPSC is that it's completely programmable in OpenCL. So you can target the on-chip cores and any accelerators or GPUs that are attached to the HPSC using OpenCL, which means that this allows you to test stuff on your desktop. And if you're running it in OpenCL, it will take advantage of whatever resources are available on your desktop machine. And then when you move it over to HPSC, it will use the resources available on HPSC. And if you're very clever in the way you do this, you're doing dynamic configuration of how many cores, threads, things like that you have, so it should be able to adapt. I have to mention Python. At the beginning of HPSC, almost 3 years ago, when I asked people inside NASA JPL what they wanted to see inside HPSC, one of the most interesting responses, we just want a laptop in space that runs Python. Okay, we got that for you. HPSC software stack, pretty extensive. This is what I would call the HPC dev software stack. I'm not really going to go through this, but just so you know, we've thought a lot about this. I sort of took all my experience and then went out and we did a ton of use case, ton of research about what needed to be in here. We also wanted it to be modern, programmable, easily accessible, not obscure, not opaque, so that you could work on this stuff in a reasonable way without wasting a lot of your time. So we think we've come up with this. And so this is sort of the culmination of all of those things. I would like to call your attention to the high-performance libraries like OpenBlast and Eigen and SQLite and XNNPack. Those are optimized for the cores that are on this machine. So I don't know how many of you are looking at flight software where you've written your 100th iteration of a matrix multiply, but no longer is that the case. You can just call OpenBlast and it's optimized to the width of the machine. You can get the fastest performance for that matrix multiply. So whatever you're doing, don't implement it yourself. Call these libraries that we have, and then you'll be assured of all the performance for HPSC. HPSC, the analysis by mission phase is pretty important. So I mentioned CDH, yes. GNC too, yes. Latency critical, minimum jitter. HPSC has a lot of features for that. EDL, HPSC has a lot of features for that. Science data processing, a lot of features for that. I won't read them, but what I will say about HPSC is it has unparalleled spacecraft command and control features. The onboard timer system, the time and space partitioning, all the fault tolerance features, it doesn't exist anywhere else. In fact, I will go so far as to say that the onboard timer and time and space partitioning features are not available on any microprocessor anywhere. This thing is purpose-built for space missions. Planning and scheduling, of course, fall protection, AI, ML as well. You can all parse this out. One of the interesting things to know is that HPSC was designed for Space VPX and the new Space VPX SOSA consortium work that's coming out, sponsored in part by NASA. That's an industry consortium to get together what a hardware platform would look like so that we can just build things out of Lego blocks rather than building them all ourselves. And I'll talk about more ecosystem at the end of this. But really the idea is that you can have lower cost, faster time to market by just getting stuff that we are pushing forward through the ecosystem. One of the things I want to call out is that HPSC kind of looks like a GPU. The interesting thing about HPSC is that it can execute scalar, vector, and AI/ML workloads all at the same time on the same cores. There's no difference between them. It's just because of the vector unit that's inside HPSC that makes this possible. So what does that mean for people who are used to using 3 tool chains to get things done with different kinds of things? Well, in HPSC, you have 1 tool chain, and especially if you use OpenCL, that's even great for off-chip GPUs. You can address that GPU with OpenCL using the same tool chain. So we are using the X280 or X288 core complex from Sci-Fi. This particular core, like I said, is designed for AI/ML. There's a lot of fancy features for the X288, which we asked for, and they put in, for us because we paid them money. Some of the things I talked about have to do with splitting up the architecture, making it very useful, adding more fault-tolerant modes. The couple biggest things are dual-core lockstep, which I mentioned already, the cluster splitting, the hashing functions. WorldGuard is very important. I'll talk about that in a second. Software virtualization. We also have CXL, which is a way that accelerators or GPUs can share the same memory space coherently with the processor. So that's very interesting. And so it really looks like 2 clusters of 4 cores each, and then you can have 4 pairs of dual core lockstep. All of these buses down here are very wide and very fast. So for flight software types in the room, who I'm assuming is everyone, HPSC has a lot of close memories. Now, what does that mean? That means that, as you all know, the relative time of everything is super important, and accessing stuff off DRAM takes a long time, but accessing things that are right next to the core don't take so much time. So these closed memories have a very small cycle load-to-use latency. There's something called the ITIM, which is 32K instruction cache. You can put often used things inside this cache. And then the data and results can be stored in the DLS, which is a data local store. There's 128K for each core. And then if you put HPSC into a cache isolated mode, you can use the L3 as a scratch pad, which is kind of interesting. So if you want to do mixed criticality, if you've got very tight loops, if you want to guarantee that there's minimum jitter, or more, you want to force more deterministic latency into the system, you can use these closed memories to address some of your concerns about instruction bubbles, latencies while traversing across the NOC into DDR and other things like that. Here's the big example. I know this looks crazy, right? You're like, this is crazy. It's very colorful. So this is an example where HPSC is split down the middle. The left-hand side is running Linux in SMP mode. And that can be, running CFE, CFS, or F prime, or whatever frameworks that you want to run. You can take advantages of all the things that I've talked about so far. And on the right-hand side, we have a split with 2 DCLS pairs running VxWorks. So right-hand side, mixed criticality, deterministic latency is very, is very controlled. On the left-hand side, Linux is Linux, so it's not very deterministic, but it is relatively high performance. So, you're sort of landing the spacecraft on the right-hand side, but on the left-hand side, as you look down in the camera to find out where you're landing, AIML is recognizing features and things, passing that back to the flight's software side to figure out where the best place to land is, basically. So these two things working in concert is a mixed criticality example. You could also use this example as a high availability failover. So if you're running, on the right-hand side, if you're running 2 of the same operating systems, one is sort of the leader and the other one's sort of the follower. If the leader dies, for example, the follower could take over under flight software control. HPSC has the best notion of time in the entire universe. No, okay. HPSC has an amazing notion of time. There's 3 onboard timers. And between these 3 onboard timers and the ability to synchronize between the timers, it is possible to keep track of very, very, very small timescale events and also coordinate command and control across cores, even in split modes. Not to mention that we have this thing called the airing block, which I'm going to talk about in a second. The airing block is tied to something called the application DMA processor. What this really means for you is that if I have an airing 653 schedule, major, minor, subminor frames, and I have DMA transfers that can only occur in certain windows, you can force the hardware to squelch or prevent DMA transfers from happening outside their window. So that's really important. The other thing I should say is one of the interesting pieces about HPSC, which I love, is the notion of this M-time register, which is precisely the same at any instant on the device. So if I'm running completely different operating systems on many places in the chip, and I want to grab time at the same place, even though I'm running different OSs, that notion of time will be precisely the same. Precisely the same. And so this is connected to the HP timer, which is a 64-bit monotonic timer with 20 nanosecond resolution. That thing's always counting up, never going backwards. Even if I take a core out of contention or I do a warm reset, I still get back to where I need to be with that value. This allows coordination of lots of very short time scale, or it allows coordination between different parts of the chip using different operating systems. Very important. VxWorks can also use the airing block to clock its execution. So here's a view of the airing block. There's a couple registers, as you can see here. And what this allows you to do is do like I said, major, minor, subminor frame stuff. But at the end of a subminor frame, for example, if I want to cause an RTI, I can do that. At the end of a major frame, if I want to wiggle a GPIO, I can do that. Or if I want to attach this up to the DMA engine, I can absolutely do that too. So between this is our time partitioned piece. We also have a space partition piece, which I'm going to talk about in a second. Or if I want to attach this up to major, minor, subminor.
I think this is what I was waiting
It allows
for.
coordination between different parts of the chip using different operating systems. Very important. VxWorks can also use the airing block to clock its execution. So here's a view of the airing block. There's a couple registers, as you can see here. And what this allows you to do is do, like I said, major, minor, subminor frame stuff. But at the end of a subminor frame, for example, if I want to cause an RTI, I can do that. At the end of a major frame, if I want to wiggle a GPIO, I can do that. Or if I want to attach this up to the DMA engine, I can absolutely do that too. So between this is our time partitioned piece. We also have a space partition piece, which I'm going to talk about in a second. This allows you to have very strong protection for time and space. One OS can't run over to the other OS, and since you can split HPSC in various different ways, it's very difficult to force HPSC to have contention all the way through the device, all the way out to the peripherals. One of the reasons why is because there's something called WorldGuard. WorldGuard is a way to guarantee that, so I'll take a step back for a second. An SoC is a bunch of disparate pieces connected by this thing called a NOC, a network on chip. It's like a big crossbar switch. And so the CPU is connected on there, the DDR is connected on there, the PCIe ports are connected on there, serial ports, all these things are connected. So you can say, hey, I want to make it so that for this side of HPSC, I only want to use this DDR interface, and I want the memory map to look like this. And for this side of HPSC, I want the memory map to look like this. I want to use these peripherals. And the great thing about this is, if one side tries to use the other side peripherals or memory, it's not possible. Not possible. So here you see 4 WorldGuard regions where some of these things are shared. For example, in World 2, you see World 2.3 data as a shared piece.
Yeah, I just wanted to give you a 2-minute warning.
Oh my God, I'm so far behind. Yeah, so At least you didn't come up here and like mess with the computer. That's okay. I'm happy to be out of time.
I'm trying.
So this lets you basically control access to HPSC peripherals. And this is not something that is a software thing. This is built into the hardware all the way up through the cores down to the very end. So it's impossible to violate it in any way. There's no software way to get around it. AppDMA is pretty impressive. We have 2 AppDMA engines. Each is an 8-channel direct memory access controller. The cool thing about this is you can set AppDMA off on a task to take some memory from someplace and put it someplace else. But in the meantime, while it's doing that, it's going to rotate it, flip it, transform it, do all this other stuff to you. As you all know, when you ingest sensors into the spacecraft, the way that it comes in is not the way the processor likes it. So this lets you put it in the way that the processor likes it behind the scenes without CPU control. CPU messing with it. So by the time the CPU has to mess with it, it's in exactly the way it needs to be. We also have AML support, TensorFlow and XNMPAC. So the cool thing about HPSC is it's got these 4 instructions, which make it possible to do, for certain types of matrix multiplies, 1 teraflop of performance for 8-bit CNNs that use 8-bit resolution. That's pretty impressive, considering that this device only runs at 1 gigahertz. HPSC has an insane debug system. It's the best that I've ever seen. There's also a possibility to debug HPSC in space. If you email me or talk to me after, I can tell you more info about this. One of the great things, and thank you so much. After, I can tell you more info about this.
Sci-fi. Freedom.
If you email me or talk to me after, I can tell you more info about this. One of the great things, and thank you so much, Microchip, is You know, HPSC project asked for these very extravagant, kind of slightly expensive evaluation boards for us to test out in the lab. But Microchip said, nah, we got to make this thing available for cheap for people. So this is a 3K eval board, which you can have on your desktop. And it gives you access to, I would say, 86.375% of all the features on HPSC. So you can put this on your desktop. You can have HPSC on your desktop and develop for it, no problems.
Yeah, so we are unfortunately out of time.
Okay.
But I do want to give you another 20 seconds if you want to say any parting words. And
yes.
All your slides are available online, and people can continue
Excellent.
the conversation on Slack.
So what I will say is HPSC loves you, loves all of you. There's a NASA white paper if you're interested. There's also the Microchip website. And I made a soundtrack about what HPSC would sound like in space. Feel free to go listen to it. It's very moody ambient music like me. So I guess that concludes my remarks. If anyone has any interest in HPSC or you want to talk to me, you can come up after. I'm happy. I'll be here most of the 4 days, I think. Do we have time for questions or did I burn all the time?
I think we went through all the time.
That's okay.
But there are questions on Slack, and so we can answer them on there.
Okay, perfect.
Thank you. Appreciate
yeah,
it.
Thank you.
Next up, we have Jim Fan. You all know him. Come on up, Jim. Jensen was talking about him just this morning. He is not only director of AI at NVIDIA, but also distinguished research scientist, and he'll talk to us about physical AI.
Or from a machine's work, right? Simple enough, the physical Turing test. But where are we now? Are we getting close?
All right, I believe the time has come for us to end our well, the time has come to call it, basically, for tonight. What is Palantir up to now? Okay, watch this later. Yeah, okay. It's time to call it. Long night. Yeah. Not a whole lot to say except if you're watching this and this was useful in any way. Well, at least the actual reading source code part. Everything else after that was mostly just watching stuff and being exposed to some new ideas or whatever. Anyway, if this was useful in any way, just like and subscribe, and I'll see you around. Have a good night, or depending on when and why you're watching this, have a good rest of your day.